Hi, and welcome back everyone to our little oreboot hacking session. So today we're going to pick up again the attempt to memory map the SPI flash, which when we tried it last time hadn't really worked. And dramforever thankfully figured out why and how it would actually work. And what I have open here now is the schematic of the board. So this here is the SPI flash just schematically. So in reality it looks a bit different. So you would have a chip with 8 legs, and I can actually show you one because I just soldered one the other day. It would look like this one here. So yeah, you would have an 8-pin chip, and out of those 8 pins, not all of them are necessarily used. So there are different variants of using SPI. There is a few pins which are always in use because they have to. So that's at least always the voltage. So you would have VCC and ground for the power supply, right? And then you would have a few data pins. You would have one for the clock and one for writing in each direction. So those are the MOSI and MISO pins. And then there are a few others which can technically be used for different purposes. One is the chip enable pin, and the chip would be enabled when the power is low. So essentially when you have ground level on that pin. This is known as active low also, and that's what you see here. It's called CE, and the bar above here, that means it's an inverted signal. So this line being active would mean that it's actually on a ground level, so it's a low level. Well, and as dramforever figured out, we can actually configure the QSPI controller. So QSPI is actually quad SPI to use our chip in a slightly different way than you would usually do it. So usually you would try to go to a high-speed mode. But for a first trial, we can go with the low-speed mode. And in that low-speed mode, you would only need a single pin for reading data. And let's actually have a look at that. So there is some nodes here in this hackmd. And in this hackmd, we will first of all find again the boot process. That's what we also discussed a few times in previous streams. And then there is this nice section here on the peripherals and other ports. And the main one that we're going to look at for now is this one on the SPI flash or QSPI flash. Now this is referencing to a few buses which are related. One of them is the Advanced High Performance Bus, or AHB. The other one, the Advanced Peripheral Bus. And both actually come from the ARM world. So yeah, that was a specification that started with ARM, but it looks like it's also being used in other places now. So yeah, the overall thing is called the AMBA, or Advanced Microcontroller Bus Architecture. Yeah, if you want to read up on that, yeah, just search for AMBA and ARM. You will just get to this article with your favorite search engine. Yeah, I've just edited the notes here so that those are links to the specific sections in the Wikipedia article. Anyway, so there is a few things we will need to do now, and we will add that to our code in order to enable us to read from here. There is a few more things which are not yet fully in here, but I dropped those notes here. Let's just close this for the time being. I already prepared a few things because last time we attempted to boot from flash directly, and this time we will see that we do it actually from right from DRAM again. Not from DRAM, sorry, from SRAM again. so that we are a bit more flexible with iterating. And for that, we will need to see a bit about the USB devices we have here. So if you recall, we have multiple pin headers. So there are two on which we can find the same serial port, and that can be configured on the board to be either on this or on that header. Yeah, so I need multiple devices and shuffle them a bit. Anyway, so to look at those nodes here, dramforever wrote, if you just set up these clocks here, PLL0 out for the CPU and D bus route, and the per H0 route, I guess that is peripheral something. Yeah, so this is coming from the vendor's code. And then you would need to tell the QSPI controller to use a specific read command. And to tell which read command to use, you actually just write that to a specific address. And this address here, 1186.0, that is what we find, that is what we find also here in the nodes. So 1186.0, and then there is +4 here, right? +4. That's a bit of an offset. This is what is also happening in second boot. Okay, so now we need to figure out how we can actually do this mode switch here. So this is a macro that we would find in second boot, and let's have a look at that again. So let's quickly find the code again. So this here is second boot, and let's search for this. So we find this in bootmain.c, right? Line 142. So that would be here, line 142. And then there was the second thing, that one here. So let's see if we can figure out what those actually do. So since I just did a search, we can look at this here, this header file, the clockgen control macro. And so we already figured out that in the current oreboot code, we have generated code which is actually coming from those headers. So we probably have something which already was translated from this macro. So let's have a look actually in oreboot if we have this clockgen control something. And for that, let's see, so above we still have the file open that I looked at last time. That is here from the SoCs directory. And there is also something called clock. So let's have a look at that. And let's see if we can find what we are searching for. So again, that was switch clock, whatever, with CPU and D-bus. And indeed, we find something around clock, whatever, and D-bus something. And there is a few things here actually. So let's see if we find exactly this function. Yes, we have that. Oh, and look at this here. The init core clock function here is already doing that. And where is that function used? Well, this is here in clock init again. And in turn, clock init is being called when we say on for the clock driver. Now let's have a look at the main code in oreboot if we have that enabling of the clock driver. So I'm going to expand this here again. Yeah, down here we would see minicom at some point, but let's not care for now. So do we have the clock init? Yes, we have that here. And I left a note here that it actually breaks when running on the VisionFive. So now let's do the, so if we run from SRAM, right? So let's do the following. That same issue was also with the IO pad control. So I will comment this out for now, because I don't want to be concerned with this for the time being. And now for the clock, I want to narrow it down to just enabling the two things that we're actually looking for. So we're going to reduce this driver a bit, and we're going to say, if we say on, instead of the full clock init, I actually want to do this part here, init core clock, and even here, I actually only want to run two functions. So let us comment out those here, and let's then run init core clock, where initially we would have run the full function. So we're going to say self.init core clock here, and comment this out. So I want to make sure that, you know, if we just run these two functions, we can still successfully boot. So I did one more thing in advance here. I modified the script a bit, or actually I copied over the script that we were using last time for loading something to SRAM and then running it. So that would be calling the JH7100 recover tool. And I just put that in the BeagleV directory here so that I can just run it directly after running make. So this is now a part of the script. And then we would load this to DRAM and run it. So you can already see there is TTY USB 1 here now. I currently have two devices attached, TTY USB 0 and 2, if I remember correctly. Yeah, so that happens when you plug in and unplug devices again and again. The enumeration can change. Anyway, so I need to make sure now I know which one is which, because I just did this with, you know, turning both of them on. So let's see. Okay, now we're left with USB 0. So I will adjust my script a bit here. This here is USB 0. And now we're going to run picocom again to monitor what's happening. So we're going to run the run script, and I will turn on the board again, and I will hit the boot mode button. Okay, so this is now looking fine, and now we should actually see something here on the second UART. Now the problem is I already had this closed. Oh, my screen is too small. Okay, then let's make it larger. Okay, so that looks better. We're going to repeat this here. Okay, well, and we actually do see something, and that something we see is happening down here, which is interesting. So, I have my suspicion. So yeah, we we did this here with the UART init. I would just skip the init here for now. So the init is supposed to not just initialize the UART, but also to switch to a different mode. So this here is running on baud rate 9600, and that thing here would actually switch to a different baud rate. So yeah, we're going to repeat this yet again. This time we're remaining at the low baud rate, and let's see if we actually see something. Yeah, we do actually, but it looks a bit weird. Okay. So yeah, now would be the time to figure out what's actually wrong there. Huh, interesting. So the good thing is that we don't see nothing, right? And I was actually hoping to see something down here, but we don't. For the record, that enable clocks and write one register mentioned earlier was basically found by trial and error with what the vendor does, and it's probably not the optimal configuration. Yeah, so yeah, we already figured this out, right? So the vendor doesn't provide us with good documentation, and all we have is some code, and well, now we're trying to make the best out of it. Yeah, I'm a bit confused now though why this down here is happening. I mean, when I run make, I'm rebuilding this here, and the same is happening when I run my script. So it should actually work. Did I save the file? Did I like really save the file? Nah, maybe commenting out a few more things should help. We will see. So there are multiple things which might actually get in our way right now. So I will just comment out all the init stuff here. Huh. Fancy. Still odd things are happening. Okay, so for the sake of it, let's switch to 115/200 and let's see what happens then. Oh, right. Yeah, now we're having a bit of a problem because I'm running Picocom now with a different baud rate concurrently with the other tool. That won't work. Yeah, now this is a problem. Okay, how do we solve this? So we had figured out that, what actually do we see here? That is also a bit strange. I don't recall entering something, and I actually can't because there is nothing running here. Okay, let's quickly recap what the UART is doing in its init. So the UART init would do this here. It would run this other function UART init and then set up a different mode. And what is the UART port it's using? I think it's actually 1184 something. I think that was the UART. Do we have this here? 1184 or something? No, now I'm confusing things. Oh, right, it was 1244. But this should have been UART 3, if I remember correctly. We can always verify this, of course. So we do have at least the memory map here. 1244. Yeah, that's UART 3. All right. And so this here would still be running on this side. Why does it happen that we see garbage? That is strange. Okay, let me just reset the device and let's see what happens then. Do we actually get to see anything? No, we don't. Okay. So yeah, maybe I didn't do what I remembered. So I thought I had done recovery again. Let's quickly get back to our tools repository. And so here I have a few scripts. Not that one here. So instead of recover def, I will just make a script recover, and I will make it based on this one. So run or flash. I will copy this now. I roughly remember what is in there. Yeah. Oh. So, yeah, this here is where we would actually have this here. I see. Okay. Yeah, so this is what we want to do. We want to restore this second boot thing. In this here. So we are now going to run the recover script that we just created. And let's see if it's really what we did. Yes, this here is recover.sh. Looking good. So let's run this. Waiting for bootloader mode. We do see something up here. And now when I reset again, I want to see something on the left-hand side. Clock thing again, if you change the clock settings, it also affects the baud. Oh. Oh, wow. Okay. Then, in that case, we should get to the point where oreboot would actually use a different UART so that we can use one for the recovery. We can monitor it loading, and then it would still work. And it looks like we were successful in what we did. Let's hit reset. I don't see anything on the left-hand side here. And this is interesting. Why do I see fancy things happening on the left? That should be the other USB device. So this here should be the second header. I don't see anything here. Okay, if you switch the CPU and dbus clock source thing, yeah. So you get 40 times the baud rate, so it could be 38400 baud. Yeah, so here is my conceptual problem. If we load something to SRAM, we're loading that over the 9600 baud, right? And then we execute it, then we are already connected. We would very quickly need to switch the mode to some other baud rate on the fly to see that it's actually executing fine. And that interferes with what we want to see. So can we should. So we should switch the baud rate before changing the clock setup so that we can see things fine. Just for one verification step, I will now comment out the syscon p write. I hate Rust for doing this here. This is something I would like Rust not to do when I comment out one line. Just because there was some comment up here, it would move the comment down here and align it with that one. But there is no relationship here. I always want to insert an empty line. That's the one annoying thing with the Rust formatter. Otherwise, it's just great. Try uncommenting the UART in it now. Yeah, so if I uncomment this here, now the issue would be that some more code would even be running again. So what I want to do first is I want to get back to seeing something on the UART. So that would be very simple now, I hope. Right, so if I do this here, no, I still don't see anything actually. That is strange. Huh. Oh. Hang on, the clock thing here, that is still here, right? Okay, so let's do this again. Oh, this is so much better. Okay, this is looking good, and this is what I wanted to see. Oh, wow. So, yeah, readable output. So indeed, when we say we enable the clock, then we would need to do something for the UART init. And so if I got you right, you're saying the baud rate would be now 4 times. Wait, 40 times? 38,400? No, that would be 4 times. So what is the original clock anyway? So if we look at the, hang on, what I want to look at. If we look at this here, so what exactly does it do? It says switch clock, but what does it switch to and what was it originally? Why does it have to be this complicated now? Okay, so yeah, so it's reading the current value, applying a mask and an OR mask. So the AND mask means that we're dropping some bits, and the OR mask means that we're setting some bits anew. So this here is, can also write this as B11. So this is 1 shifted by 24 to the left, but negated. So it's actually just as if we were saying 1 1 1 1 1 2 zeros and then lots of ones again, which some people don't like writing, so they do it this way. But then you need to apply like 10 operations in your head, and it gets very confusing. So if you write code like this, please don't. Yeah. So this is now, that doesn't actually make sense. I mean, why would you say 1 and 3? I can already tell you this is just 1. That also doesn't make any sense. So this here, this expression is the same as this expression. It doesn't make sense to write it that way. So yeah, we're replacing those 2 bits here, which were formerly 3, with just being 1. But this here is probably from having generated code anyway. I will just undo this here. Sorry. Whoops. I don't mean to undo this. Okay. So we're changing from maybe 3 to 1. Where do we find this? So this is on the system something that was 1184, lots of zeros. This year, reset gen? No, that was something else. Am I confusing things now? Hang on. So here in the node we have 1180, not 84. Sorry, my bad. So yeah, this is the clock gen CSR, right? And that would be maybe documented, who knows? Clock gen CSR with 1 occurrence. Okay, great. So you really just figured this out by trial and error. Yeah, so the UART clock that is currently in the code, that would set it to fast rate. That's true. So it would try to switch to 115/200. If you just initialize the UART as last time and also switch the clock source, this time it should be right. Hopefully. So you mean when I run from flash, right? The problem would still be, though, that I would be on, so, oh, hang on. No, I would still be on the same, if I don't switch to the other UART port, I would still be connected with the same USB serial adapter here with the same baud rate, and that is always... So I don't want to switch on demand. That doesn't make any sense, because then I would always need to very quickly see and say, okay, now I need to switch. That is a stupid process. So what I would actually really like to do is just keep the baud rate as it is. In other words, I would like to figure out the new divisor for 115/200. So what is this shift by 4 anyway? And can we do this? Can we figure out? Probably print in an infinite loop or something. I'm not sure what we would get out of that. So I want to figure out the right way to set the baud rate as we need it. So if the baud rate is impacted by the R&D bus or whatever bus speed here, CPU and D bus, if this here is affecting the baud rate, which actually confuses me a bit, then I would just want to know the counterpart. So maybe I can just set the new divisor, but instead of doing 115/200, I mean, this here is really just a constant 115/200. I would want to try 9600. And now the UART clock here. This is one, cannot read this, so let's group that. So this is 100 million. 100 million is now somehow relative to the CPU and D bus. Oh, this is, hang on, this UART clock is suitable. So if this is the right UART clock, then this here should work, right? And so we should now, if we go back here, now we do both UART init and also the clock init this here. Now that should work, right? Let's actually see if it does. Oh wow, yeah, it did. Perfect, awesome. Nice. And do you see what I see? So we went from seeing FFFF to 0000, which means that we did get something, but reading didn't work properly. Awesome, thank you. So we're now going to commit this seriously. Git diff. So this is what we did. We commented out this here again and this here. Maybe that wasn't necessary. And also this here, but yeah, I don't really care right now. We commented out that thing and we changed the divisor. Yeah, we actually only did a few things here in the init core clock. Wow, amazing, cool. Okay, so yeah, but before commit, okay, I will commit this for now. Switch to 9600 baud on debug UART port. This is amazing. So I want to uncomment those things again, actually, because there were some things which we already had working fine. I want to see if they still do. Okay, that looks good. So this is a fix up. Now we're going to do another one. So this one here. So maybe this comment here was actually not right. Where is that one? Syscon. Where is Syscon? Oh, Yeah, that went here. Thank you, Rust formatter. Okay, so this one is breaking indeed. Now, which of the two was the breakage? Was it the IO pad control or was it the other one? That's easy to figure out. I mean, maybe it can happen with both, but this here is looking fine again. So let's commit this again as a fix-up. Yeah, I sometimes write fixie fixie because a former colleague of mine did that sometimes. That was funny. Anyway, so we are now able to proceed. Yeah, should is the keyword. Yeah, it always is, but we got to this point now. Okay, so now I don't really care about anything but this here. So I want to see if we now can read from the SPI flash. If we apply the one change that you proposed here, so changing this command. So we're going to write to this address here. What do we have to call it? So glow QSPI. Oh, okay, we don't have a name for that yet. Anyway, so let's define a const. So we say const something which is a usize, and that gets this value. I'm once again a bit unable to type. So that's 1186 quad 0, and let's see what they call it here. 1186 quad 0 is QSPI CSR. Yeah, right. So QSPI CSR, and now we define the next const, which is QSPI read command, and that would be QSPI CSR plus OX0004. And now we're going to write to the QSPI read command register a very stupid value. And we're going to do this after running the clock setup. So the way we're going to do this, first of all, this needs to be unsafe. Basically, when you do low-level firmware in Rust, you just put unsafe in lots of places. It's not something you should do, but in very many circumstances here you would have to, because you write to arbitrary registers and Rust cannot know what those registers are related to, right? So yeah, it just looks like you're writing to an arbitrary memory address, which is not desirable. But since we're doing memory mapped IO, we need to know what we're doing in this instance. So we're saying write volatile. We're using QSPI read command as a star mute U32. So it's a 4-byte value. We're going to write OX0003. So this is the read command in SPI. Well, for SPI flash. And now if I was able to type, I would actually make parentheses. Oh, right. The curly brace was fine. I was just missing the closing parentheses. Okay. And we can actually also say this is SPI flash read command, and then also make it a const. So we say const SPI flash read command. This is now U32, and that is OX0003. Excellent. So let's see if this works. Run it. And look at that. Amazing, we were able to read the value. So this year, EC24 something, this is now read from the SPI flash. So this address 2000 quad 0, this is where the SPI flash starts, where we previously just got 0, 0 and so on. Woohoo! Thank you. So now that we have that, let's commit this. Git commit map SPI flash. Yeah, this is not the time for writing very nice commit messages. Usually we would prefix with, you know, whatever the scope would be and so on. So yeah, these are now crap messages. Usually we would write something like this year or whatever, right? So yeah, we do have mixed formats of it, but never mind that. Anyway, this is awesome. What it means is we can now run the DDR init from the vendor code, which is what we're reading from this address here, 2001 or 4K. So at the 4K offset, this is where they put the vendor's code, but it's starting with the first byte being the size. Yeah, so that was the DRAM blob size at that address, and after that comes the actual thing to read, and DRAM blob size tells us how much to read. And we're reading these in steps of 4, so 4 bytes each, and we just put them somewhere else in memory, this year somewhere else in SRAM. And then we're now going to uncomment this here. We just call it directly and then see what happens with the rest of the boot flow. We should probably see something more down there from the DDR init. Let's see. And it says jump to something, but then we don't get any more output. And I guess that is because we were switching. Oh, look at that. There is something down there. It's just that we cannot really see it because baud rates and so on. So I want to run this again and see if we get something on the other UART. Oh, wow. I guess the device is being a bit confused now. It's looking funny though. Or maybe it's just PicoCom. Oh, looks like it was writing something. Anyway, it looks like we were executing code. Yeah, I will just turn off the device for a second. Yeah, somebody was actually writing that they had an issue with U-boot getting lost when they were using the vendor's tools for flashing. So currently it doesn't look like that to me, to be honest, but you never know. I mean, it does in part look a bit like that. So I just restored the vendor's binary, right? And did we actually run that? I thought so. Anyway, we do get some output again, and I want to do a few things here now because this does not really help us. First of all, this here, a line break. Another line break here. Oh, and a line break before this. It should be a bit more readable again. Or so I thought. And let's try again because it's always so much fun. Okay. So yeah, that was missing the line feed. Wait, this is carriage return, this is line feed. Okay, that looks good. Okay. And now this is garbage again, so let's just do this one more time. Okay, that is a bit more readable. So what we see down here, 9712 and so on, is it's the same thing that we're also seeing here. And these previous 8 bytes here, or well, 4 bytes, sorry. This is now the size of the DRAM blob. So if we put this in my favorite calculator, Node.js, this will look like a very large number, but we actually have to read it backwards because the bytes are in reverse order. So I can just remove those. So it's actually 0155F0. So yeah, we have about 87K. That's okay. Okay, nice. So yeah, I wanted to do one more thing today. And that is, so you dropped some notes on the boot flow that you could imagine, right? And I want to get back to that. So actually, I saved the image that you've drawn. Let's look at the image. I have it somewhere here. Yeah, so this is a draft for a boot flow that we could do instead of the vendors. So there's this one thing we cannot change anyway, the hard-coded part that is here in the maskram, right? And then you were suggesting that we could start with just a few bytes here, maybe 100 bytes for a very small stub. So that would be the compiled code again, right? So that would really just be the clock setup and setting up the memory mapping here. And then we would just jump to whatever is now in SPI Flash. So I'm wondering a bit. So this here is what we could run from SRAM, right? And what would FSBL be? So FSBL, I know the acronym, so BL is for bootloader. What would FS be again in this scenario? Yeah, FSBL, blah, 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 blah. First stage bootloader, right? So first stage bootloader would be what the vendor is calling second boot. And that would be from us, right? So that's what we would write. And we would start with a DRAM init. We could use the vendor's code for, just having a blob. That is true. So what we could do is we could just strip out everything which is like writing to the UART again or something, or initializing clocks again or whatever. So we also saw that in the DRAM init they have a bit more stuff which we do not need. And then we could just run that DDR stuff and then copy whatever we have in SPI Flash to DRAM and just jump there and execute it. And there we could just have everything, the RISC SPI stuff, hand over to Linux boot. Yeah. Now, or we could use OpenSPI and UBoot, but yeah, then we would need to mess with that again. To be honest, I haven't done much with OpenSPI, and it's also a bit complicated. So yeah, we're probably just going to stick with RISC SPI because it's much easier to use. And Linux boot also, yeah, we can just execute the Linux kernel, and it's very much self-sufficient, and we already have everything there in the environment. whereas U-boot, yeah, that would need a board specific implementation again and so on. I mean, we would also need to configure the Linux kernel in a similar fashion. Yeah, but we will probably stick with this here. This is a bit easier. Okay. So yeah, that is an excellent idea. So when I was working on the Allwinner D1, I did something similar, but there is a tool which could already run a DRAM blob for me, so that I could start right here already. But this here is now something we would need to do ourselves, so we would just carve out the DRAM init part that is relevant to us and run it like a function call actually, right? And then we would need to return to our code again and then do this here, or tell it to just jump to something where we then put our stuff. That would also work. So yeah, so the vendor's DDR init is already capable of doing this jump. That is also the stock boot flow. So I would probably just see that we change their code for writing to the UART. So do we want output from the vendor's DDR init? It's not much code that is running there, and it's usually very quick. So we could just ignore that and just be happy when it works. And if it doesn't work, we would need to try to debug that anyway. I mean, it's currently working fine mostly. It might be that the clock setup that we're doing is also a bit now getting in the DDR clock range or something. I don't know. I would need to have to look at that. But otherwise, I would just expect it to work. And as we just saw, we actually do get something on the UART from that would be from the DDR init, because that's what we were currently loading in oreboot anyway. Yeah, so essentially we already have something which is very much this here. So the stub we're talking about is what we currently have in the oreboot code. Okay, so let's maybe just try to let's close this for real. Let's try to figure out if we can change the DDR init such that it would be compatible with the changes that we're doing to the bus. So I think it's also running at 9600 baud, right? So it would usually also print here to the debug UART, if I recall correctly. I mean, it does so here. Yeah. Or maybe, or is it actually expecting to be running at 115/200 on the other one again? And it's just that because we don't do the change, that doesn't happen. Okay, that is also something to figure out. Yeah, but we already got very, very far today. I like that. Yeah, another interesting thing would be to see how far we actually got today. So yeah. Would it make sense to switch back the clocks? I don't think so. We would just be confusing ourselves. Yeah, maybe we should rather port over the code that would be changing the UART to sit on the other header. I think that is much, much more convenient for us anyway in the long term. So yeah, let's have a look again at the wanted to have a look again at the at the schematic here. So we just configured the, sorry, maybe that's a bit hard to read otherwise on the screen. So we just configured the SPI controller to read from flash, and we could read out values and we could print them. That was good. And there was this other thing with the GPIO headers, or the, yeah, so the debug header, this here. So this header is something really messy on this board. I would like to be able to do this change to the other one. Yeah, for that we would just need to run these magic values that you already found as well. Again, just writing to interesting buses. Let's actually look at the nodes again. So there is there is a pin control YAML file here. So this is for the device tree in Linux, which is doing something similar. And oh, I had to translate a few things here from the vendor's code because I looked into the second boot again. That is this part. So in the second boot, they are also doing the UART init and so on, right? Yeah, I would like to get to the point where we have the same setup that the vendor's code can then also use and then can keep printing to the UART. I think that's the most constructive thing for now. Oh, and this here is also interesting. This here is copying a value from one address to another. Why ever it's doing that. Interesting. All right. Yeah, so let's see next time. I will prepare a bit for this because it will be very hard to figure out otherwise. Let's see that we next time get to seeing output from the DDR init. I will try to modify the DDR init code for doing that. And then let's see that we from DDR init jump to our own code again that we put in the SPI flash, and then continue our execution flow so that we can just say, okay, now we have DDR RAM, and we can just continue with whatever REST SPI and Linux. Okay. Yeah, so thank you very much. Yeah, I will end the stream for today. This time it was a bit shorter, but I hope that is fine. And I will see you next time, and then we will do some DRAM in it. Take care.